who are interested in data science, particularly in the topics which I will be presenting. Some of the topics are state of art in the sense that they have become very popular in the recent years. I'll be talking about deep learning, and I'll also tell you something about the work that we have done in the last 3-4 years with my PhD students, and I'll introduce the basic ideas of dimensionality reduction or data dimensionality reduction, and talk about two techniques especially which are very popular in data science and which require a good amount of mathematical background. So I expect you are master students, most of you. So I think that you must have gone through courses in linear algebra, and you are familiar with a little bit of statistical pattern recognition, if I am not mistaken, because I feel that in this part of India we are very good at pattern recognition, especially the statistical decision theory and statistical pattern recognition. So let me start off with the first technique. Which I can scroll. How do I scroll? How can I scroll? Pointer? I have to use the laptop. Yeah. So let us start. So let us start off with principal component analysis, and I think all of you are familiar with covariance matrices, and you are aware of how to take the eigenanalysis of a covariance matrix. So the principal component analysis is basically using second order statistics of data. So when I say second order statistics, I mean the correlation or the covariance, the variances of random vectors or random variables. So suppose I have a large dimensional data point. For example, I have based my slides around hyperspectral image processing, so I don't know how many of you are doing hyperspectral image processing, but you might be aware that these days we have remote sensing satellites up in the space, and they capture several bands. So we have got band 1 to band n, and each band is an image of size, some rows and some columns. Generally we take it as m and n. So let us look at one particular pixel across all bands. So if I look at one particular pixel, that is called the pixel vector. So this is a pixel vector, say at location I comma j, and I can now look at the intensities at this particular location in all the bands, and I can stack it up as a vector. So this bold notation is for a vector, and this is at particular location I. This I is a two tuple, stands for I comma j. So x1 to x capital N, and you can have several such pixel vectors. I will call it as a pixel vector because it is at a particular pixel and it's a vector. So it's a pixel vector, and I can have rows into columns, number of pixel vectors. So we will have such dimensionality in the data, and I want to reduce this dimensionality. That is, I don't want all these n bands. I want less than capital N bands. That is the whole idea. What should I do so that I can throw off as many bands as possible without losing meaningful information in this data? Okay. So one of the techniques that people use is called the principal component analysis, PCA. PCA has several flavors. What I I will introduce is the very basic analysis. What it does, it's also called KL transform, the Carr-Hunen-Love transform. Okay. So people in the compression, image compression domain use this KL transform as an optimal transform. It is optimal in what way? Okay. And what does it achieve? After you apply KL transform on some data like this, what will you achieve? You get another set of data, you get the transform data which is decorrelated. So suppose this is image data is notorious for having correlations. Okay. Any image or any natural signal contains correlations because data is related statistically around a neighborhood, a spatial neighborhood here, and also across bands. So there is a spectral neighborhood and there is a spatial neighborhood. So we talk about correlations in natural signals which can be images, which can be speech signals. So why should there be correlation, and what is that signal which is ideally non-correlated? So what is that signal which you study in statistics, which you can call as the ideal of non-correlatedness? Can anybody tell me? When the students, like, are you aware of some kind of a signal which doesn't have any correlation among its samples? Anyone? Haven't you heard about noise? Have you heard about noise? Have you looked at the statistics of noise? What types of statistics have you looked at in noise? Is there a special type of noise which I am referring to? Can you name that noise? Gaussian is the PDF of that. What is the statistical characteristic? This is a word to describe that. Okay, so it is white noise. So when I say white, I mean that the autocorrelation function is a Dirac delta. So if the autocorrelation function is a Dirac delta, that means the pixel I comma j is not related to pixel I comma j plus 1. Okay, so there is no correlation in the samples and it is ideally a non-correlated signal. So ECA decorrelates data. So we will have a transformation where if you consider this as x, I will get a vector y which is related with x in a linear manner. Okay? It is not a non-linear transformation, it is a linear transformation. So the mathematics is linear. How can I describe a linear transformation? If I want to transform a vector x linearly, what should I operate it with? What is that mathematical operator with which I should do something, manipulate vector x so that I get a linear relationship? How should I linearly transform x into a vector y? Simple answer, multiply it with a matrix. So a matrix transformation is a linear map. So when I multiply it with a matrix, I need to create that matrix. And that matrix is the transformation matrix which is given by the principal component analysis. What are principal components? What is that we are trying to do? We will all look at now. So we need a matrix to multiply this vector x to transform it into a vector y. And I am saying that this vector x, if you look at this particular pixel vector, and I have another pixel vector xi plus 1, which is again here, then xi and xi plus 1 are correlated. That is what I mean by correlation in data. So if I look at another pixel vector behind this, and I denote it as xi minus 1, then xi minus 1 and xi plus 1 are correlated. So what is that pixel vector y that I should generate from x which will not have correlations, which will be ideally uncorrelated data? So that is achieved by the KL transformation or the principal component analysis. It's a synonym. Okay, it's the same technique. What it does it minimizes mean squared distance between data points and projections. So suppose you have these as data points and you have these two bands. So these data points, you think of them as being some 2D points. Each of them have some value and they are at a particular location, say I, comma j. So you can assume that these are all points lying in 2D space and they have some projection onto this band and some projection onto this band. So I can write a particular vector here, say a vector x here, as equal to a times I hat plus b times j hat. Correct? I can write using Cartesian geometry, Cartesian coordinates, I can write x equal to a into I hat plus b into j hat. And I can compute that a by taking a projection of x onto this axis and b by taking a projection of x onto this axis. But if you look at here, if these are the two bands, then the projections are large. So it minimizes mean squared distance between data points and projections. So how should I transform these axes such that the projections of these data points will be least? Okay. Or the minimum mean squared distance between data point and projection will be least. If I project from here to here, the mean squared distance between here to here is this line, this vector. Similarly, if I project from here to here, this is the distance. But if I transform this axis from here to this, the red one, then my projection is from here to here only. And if I correspondingly transform this guy from here to here, then my projection is only here. So if I square the distance and sum, I will get less distance between the data point and projection. So it minimizes the mean square distance between data point and projections. It finds the optimal direction to represent data. That is the way to put it. So it transforms the bands, the original bands or the original Cartesian coordinate frame or the coordinate frame with which you represent that original data into another coordinate frame where the representation of data is much more efficient. That is why that transformation is called optimum. So let us now look at the mathematics and understand how we can compute a matrix with which to multiply x to get y. So given data points in an n-dimensional space, when I refer to an n-dimensional space, what am I referring to? For example, I am referring to a vector space which has how many coordinate axes? N, capital N coordinate axis. So suppose I have 3 coordinate axes, I can represent a vector in that space which is denoted as R3 using 3 projections or 3 components. So 3 tuples. Right now I have an n tuple vector. So I need to represent this point. This vector is a point in Rn, R capital N, R to the subscript capital N. So this is the idea that you are given such data points and this data is huge. It is having huge dimension. I want to reduce this dimension. How to reduce this dimension? I want to come to another space where I can throw away some of the coordinates. I can remove some of these data points. I cannot remove it from x. If I remove it from x, I lose meaningful information. So I have to transform x into something which is y, such that all the meaningful information is packed into some of the coordinates of y and non-meaningful information is remaining in the other coordinates which can be removed without losing information in x. So this is the notation, capital N here, capital N number of bands, and we are looking at different points in the bands at one particular pixel coordinate, that is I, j. So this is bold I. That means it is a 2 tuple. Bold I is equal to I, j. I don't have a bold here, so I can't write. That is. Okay, so if somebody can put it up, I can try to So now we can find the mean vector. Suppose there are several such points. There are n different points, or capital M number of different points. So if I have such capital M number of n dimensional vectors, then I can find the mean vector to represent these vectors in some cluster. This is some kind of a centroid of that cluster. You can think about it. So the mean pixel vector can be written like this. Very simple thing. So now comes the covariance matrix. So I want to compute the covariance matrix. I hope everyone knows about the expectation operator. So this operator is coming from statistics, and so suppose I have a random variable x and it has a PDF denoted like this, then the expectation of this random variable x I hope all of you are familiar with this, and we can derive the covariance matrix of this particular random vector. This is a random vector, okay? So this is the mean vector which I showed you in the previous slide. So expectation of x is the mean pixel vector. So I can take the expectation of x minus mu x, so I can find the mean, and this is also, by the way, the mean. The expectation of x is also equal to the mean of x. So to find covariance of x, I just have to do the expectation of x minus mu of x into x minus mu of x over transpose. So this is actually the outer product of x minus mu x. X minus mu x is a vector. So I take the outer product of two vectors. What do I get? If I take the outer product of two vectors, what do I get? If I take the inner product of two vectors, what do I get? If I have a column vector, say of size 3 points. So there is a vector A containing 3 points, and it's a column vector. So what is the dimension of that? 3 by 1. So if I have to take the inner product of that vector with respect to itself, what do I get? 3 cross 1 into 1 cross 3, that is equal to? That is equal to 3 cross 3. How? You forgot the transpose. This is the inner product. Okay, it's also denoted like this. So if this was a 3 cross 1 column vector, the transpose was?
3 by 1.
Transpose was? And B was also a 3 cross 1 vector. So what do you get? A number, scalar. Okay? So inner product leads to a scalar. If I just shift that transpose to this vector B, so I talk about A into B transpose. What do I get? A is 3 cross 1, B is 1 cross 3. I can multiply, and finally I get a 3 cross 3 matrix. Therefore, I also get a matrix. I am taking the outer product of x minus mu x with x minus mu x transpose. So I get a matrix. So that matrix is called the covariance matrix. This covariance matrix is capturing second order data, second order statistics of x, because I am using mean and I am again taking a expectation here. So this leads to second order statistics. I am actually calculating the covariance matrix. So now there are capital M number of points, and this covariance matrix has to be computed. So this vector expectation of x is composed of capital M number of points summed over how many points inside each vector? N cross 1, capital N cross 1. So what will be the size of this matrix? Capital N cross capital N, isn't it? Because this is of size capital N cross 1, a column vector. This is also a capital N cross 1 column vector. So I take capital N cross 1 into 1 cross n. I get capital N cross capital N. So that's a covariance matrix size. So what is the size of that covariance matrix you see? So if today you are talking about satellite imagery, where for some cases we have maybe 200 bands, and each band of size 1500 cross 1500 pixel, then what is the dimensionality of the data we are looking at? We are looking at 200 into 1500 into 1500. Okay. So that is the kind of data that we have, raw data from the satellite imagery, and we are supposed to analyze that. So if you are going to analyze that, you are going to use supercomputers. How can you analyze with desktops? So you have to use principal component analysis, which will throw away redundant information in the imagery, and it will keep only meaningful information. So how to transform that vector x into a vector y? That is the idea. And that transformation has to be the optimal transformation. So we have this particular covariance matrix. This can be obtained not by using this ensemble statistics. This is expectation operator is ensemble statistics, right? I talk about random variables, I talk about random vectors, I talk about such things. I am given only one sample of the data. Have you studied ergodicity, the ergodic nature of data? Have you come across this term? Or ergodicity. If you invoke this, then it means that you can approximate. So all of you know about a random process, right? You have studied about random vectors, random process. You know what exactly is a random process. You switch on your radio receiver when it is not tuned to any station. What do you hear? That is noise. You plot it on an oscilloscope. What do you see? A waveform. Okay. That waveform is random in nature. So suppose I have 100 different receivers in this room, and I turn them on simultaneously. Okay. So what do I record on the oscilloscopes? 100 different oscilloscopes. 100 different receivers receiving some particular frequency where there is no station, where there is no meaningful information. So it is receiving galactic noise, or whatever you say, that whatever is coming on the channel, that noise. And there are 100 such receivers, and you will get 100 different waveforms. So if I want to compute the mean waveform, I will use this. That is the ensemble of those random waveforms, and I want to compute the ensemble or the expectation of those waveforms. If I sample those set of waveforms at one instant, what do I get? There are 100 waveforms. I sample it, all the waveforms at one particular instant. What do I get? When I sample a random process at one particular instant, I get a random variable. And because there are 100 waveforms, I get a random vector. That is this random waveform. So you can imagine these n bands as data coming from maybe 100 satellites. Okay. And you have such huge amount of data available to you, satellite data. If you take the mean over such huge data, you will actually derive this ensemble statistics. But you don't have 100 different satellites data. You have only one satellite's data. Okay, captured at some point of time. So you will invoke this guy. That the data has the property of ergodicity, and you can estimate ensemble statistics with deterministic waveforms. So once you have recorded that waveform, it is deterministic. It is no longer random, right? data, so there is nothing random about that data. Suppose you would have captured that data again tomorrow at the same place, at the same time in the day, you will get another image of that same location. Suppose there was a satellite on location, some point when the satellite was going like that. So you took on the first day the satellite imagery, the n bands at one particular point in the day at one particular location of the Earth. And then again it came back next day and you took another data. You will get the same data, and if you capture it like that for thousands of days, then you will get actually ensemble statistics. That is a real covariance matrix that you can compute. Right now what I am doing an approximation here is I am using the data which is recorded and computing the covariance matrix from that data by invoking this guy ergodicity. So I say that my data is ergodic in nature, so I can take only one waveform and find its mean and say that that is the mean of the ensemble. So I will approximate that and say that this is my covariance matrix computed from the data itself, and data is given to you. That is the satellite imagery data that is available, which I showed you in the previous slide. Now, if you have this covariance matrix of the data, then what should I do with this covariance matrix such that I get an optimal transformation, an optimal matrix with which to multiply x to get y, which is decorrelated. Turns out that I can do an eigenvalue decomposition of this covariance matrix. And when I do an eigenvalue decomposition, I will get a product here like this, which is A into D into A transpose. How do I get this? What do I do? How did I obtain this? Have you heard about similarity transformations? Similarity transformations in mathematics, in linear algebra. So if you have a symmetric matrix, how can you diagonalize that matrix? Or how can you find a similar matrix? So I have used that. This covariance matrix is supposed to be a symmetric matrix. It has a property that it is symmetric, positive, definite, and Hermitian in nature. Or rather, you can say that it is symmetric for real case. So it is symmetric, positive, definite matrix, and I can use another matrix which can transform this into a diagonal matrix. And that matrix is composed of the eigenvectors of this covariance matrix. So A is a matrix which is an orthonormal matrix composed of n-dimensional eigenvectors like this. So if you have a 200 band satellite data, you need 200 different eigenvectors to form this capital A matrix. And when you write this right hand side, you will be able to denote, or you will be able to get C. So you have this orthonormal matrix A, which is composed of eigenvectors of Cx, and you have capital D, which is a diagonal matrix whose diagonal elements are the eigenvalues lambda 1 to lambda n. There is a relationship between lambda 1 and A1. So lambda 1 is the eigenvalue corresponding to this particular eigenvector. So if you write capital D with the largest eigenvalue on the top left corner, then the first column vector is A1, the eigenvector corresponding to lambda 1. So like that you can arrange the eigenvalues in a descending order and you get these eigenvectors. So what do you have now? You have a representation of Cx with this matrix A with diagonal elements in D. So I can easily look at the diagonal elements and decide which eigenvectors are important, because the diagonal elements will be decaying. So if you write capital D as lambda 1, lambda 2 up to lambda n, all these elements are 0, then if you plot lambdas versus n, you get a decaying curve. So the initial eigenvalues are high and they are important to reconstruct C. If you reconstruct C, you have reconstructed X, because you have derived Cx from X1. So the eigenvectors are important, I can throw away the later eigenvectors. So that is the idea of decorrelation. That is, you have decorrelated vectors which you will obtain by multiplying A with the mean subtracted data vector xi. So this is EC. This is the linear transformation. So you calculate the eigen decomposition of Cx and you find the eigenvectors of the covariance matrix. You arrange the eigenvectors along the rows. Okay, this is A transpose. So arrange the eigenvectors along the rows and multiply that matrix with the mean subtracted vectors. So I goes from 1 to capital M. So you have, now this capital M is equal to rows into columns of that image which I showed you. So there are rows into columns into bands, amount of data. Now you have got yi here. What is the speciality about yi which is not there in xi? So let us analyze. So as I said that initial eigenvalues are high and other eigenvalues are low. So what I will do is I will write this vector. This is zi. It has only capital K number of capital K number of elements. Instead of capital N number of elements in X, this Z vector has only capital K number of elements. What have I done? I have taken these rows which are the eigenvectors in A matrix and I have kept only K rows. That means I have removed the eigenvectors beyond this. All eigenvectors corresponding to eigenvalue greater than lambda k are removed. Because the eigenvalue lambda k is small enough, I can remove the eigenvectors beyond that point and I will not incur error. In fact, I can actually calculate how much error I incur in reconstructing back x. So this is a reversible transformation, right? So if I can get from x y by using A transpose, then I can get back x by multiplying what with y. And what is the reason for that? This is a forward transformation, right? I am able to reconstruct yi from x by using this matrix A. How can I get from yi x? What should I do? I'll give you a hint. This A matrix is orthonormal. So what should I do to yi if A is an orthonormal matrix to get back x? What is the property of an orthonormal matrix? It's equal to? So how can I get back x from y? Just observe. What do I get? What do I get here? So this is the advantage of choosing a linear transformation, a transformation with which you can reversibly obtain the data vector from where you started. So what I have done is I have effectively reduced the amount of bands required to represent x. Right now I require capital N number of bands. Here I can do away with those bands which which are greater than capital K. So I will retain only capital K number of bands, where capital K is much less than capital N. So suppose you have 200 bands in your original satellite data, I will keep only the top 3 bands. That means I will keep only Z1, Z2, Z3. Those are the first 3 data points corresponding to the first 3 eigenvectors, corresponding to the first 3 eigenvalues. Because it turns out that this curve is very, very steep. So lambda I goes to 0 very, very soon. So in fact, the first lambda is the greatest lambda, and I will show you for real data how you can visualize. Just give me a second. Okay, so we can actually see that for real hyperspectral imagery, you can keep only the first 3 bands or the first 3 components here. You can throw away all the other eigenvectors, and it really doesn't matter. So this is the idea of principal component analysis. So first K of PCF bands contain the majority of information residing in the original hyperspectral images, and the property of the transformed data is such that the first PCF band will have the highest contrast and the highest variance. Okay. So I showed you those coordinate transformations in the first slide, and I said that when you do that coordinate transformation, you are actually aligning the coordinates or the coordinate axis to the data itself. That means you are maximizing the variance of the transformed data. So the first PCF band will have the highest contrast or the highest variance, and the lowest contrast will be there in the lowest band. So these eigenvectors are linked with the amount of variance. The eigenvalues are actually linked to the amount of variance in the bands. So I can compute this factor, the percentage variance in the ith band, by looking at this ratio. So suppose I want to compute the percentage variance in the ith or the first band, then I will do lambda 1 divided by summation of all eigenvalues into 100. That will give me the percentage of variance that is preserved in the first band. Similarly, I can calculate the percentage of variance that is preserved in the second band, like that. And you will see very soon that this percentage will fall off very, very sharply. And after the third eigenvalue, the percentage is almost 0. So we have preserved the maximum amount of information in the original data by doing PCA. So some of the references, if you want to write it, you can write it down. Refer to these papers. There are very nice books about PCA, but they don't talk about it from the hyperspectral image processing point of view. So some of these papers you can refer if you want to understand how to translate the mathematics that is there in the textbooks to actually hyperspectral image data. So let me just go to our results and some of the actual hyperspectral data. So if any of you is exposed to hyperspectral image processing, they would have known what is this Indian Pines data. Have you seen this Indian Pines data? Anyone? So you might be aware that this contains how many bands? How many bands? It has large number of bands. Okay. Maybe not 200, less than that.
156.
So it has large number of bands. And I want to reduce all those bands to only these 3 bands. And why should I be able to do that? Because of this fact. So if you look at that ratio which I showed in the previous slide, I am computing this. So lambda 1 by summation of all lambdas. Lambda 2 by summation of all lambdas. Lambda 3 by summation of all lambdas. So let me see. What do I get? For the first band, the amount of variance that you capture in the first band is 68%. That's why it looks the brightest. Huge contrast. Variance means contrast is good in the image. Similarly, you look at the second one, second TCF band. This is lambda 2 by summation of lambdas. That comes to 23% only. And the third one is only 1.5%. So it is looking so dark. The image is looking dark because the variance is less. It's only 1%. So I need not keep more than the third band. So my Z vector, whatever I showed you, contains only 3 components. So I am throwing off all the eigenvectors after the third one. And from this 156 whatever number of channels that you said, I arrive at only Z1, Z2, Z2. I arrive at only 3 bands. So this is our PC analysis of Indian pines. Similarly, you can do it for another data which is pretty common. And again you observe the same kind of variation. So this is about data dimensionality reduction. So where we had capital N bands into M rows into N columns data, we have now only 3 bands into capital M into capital N number of. So this is dimensionality reduction with PC. I will go to the next technique. By the way, what time do you want to have your lunch? Just give me an idea, I will schedule my slides accordingly.
Sir,
When do you want to go for lunch?
all the characteristics are present in this 3 band.
Yes, all the characteristics will be present in these 3 bands. If you take the 4th band and the 5th band, they contain almost more data. So whatever analysis you want to do, you can do with these 3 bands. That is a big advantage of PC. You can actually calculate what is the error that you incur in this formula. You asked a good question just to convince you. So I have this from A, I can reconstruct X. Now I am telling you that keep only 3 rows in A, not more than that, only 3 eigenvectors. Then what is the error that you incur? The error that you incur in calculating X in the mean squared error sense, okay, mark my words, the error that you incur in reconstructing X from Y in the mean squared error sense is just equal to summation J equal to 4 to capital N lambda J. And what is that lambda J? It's close to 0, isn't it? I've already showed you that lambdas are decaying like this. So after the third eigenvalue, the values are almost 0. So it has been proved that the mean squared error that you incur in reconstructing X from Y, which has been obtained by using only 3 eigenvectors in A, is equal to summation of J equal to 4 to capital N lambda J, and that will turn out to be a very small number. So you will be able to reconstruct X from Y, where you have thrown away 150 bands, you will get away with only this much error. So that is why people use PC. There are disadvantages associated with PC. I am not going into that. Okay, that is for another day. But let me go to another technique where you can leverage one more information. Okay, so I was asking the question, when is the lunch?
1 p.m. sir.
1 p.m. So let me try to finish the next thing. But before I go to that, let me show you for another data set what you can do. What is the interpretation of PC? So one paper that was published way back in 1992, Journal of Cognitive Neurosciences by Matthew Turk and Alex Pentland. You can refer to it. 1990 Journal of Cognitive Neurosciences by Matthew Turk and Alex Pentland. This paper talks about a term called eigenfaces, and it applies PCA for face recognition. It was the first paper approximately which talked about PCA for face recognition. That paper came after some papers by Sirovich and Kirby and all, but that was the first paper recognized which used PCA for face recognition. How do you do PCA for face recognition? I have shown you for data dimensionality reduction. Can you do it for classification? PCA for classification, recognition. How to do it? How to visualize it? Suppose you have a face image I, X, Y, and this be a n by n array of intensity values. So suppose you take a square picture, and that is one particular picture I, X, Y. And suppose you have people faces, there are say 10 people in the classroom, and you have recorded their faces under different expressions, or under different headgear, under different face conditions, for over 20 different images. So you have captured 20 images per person, and there are 10 persons in the room. So there are 200 images. So if you have 200 images, how to recognize one person out of that set? So that is the problem. And the paper that describes that is eigenfaces. So it just takes again the eigenanalysis of the covariance matrix. So the PCA will find vectors that define the subspace of all the face images, and this subspace is called the face space. The important idea here is that I will write each data point, that is each face, as a linear combination of faces which are called eigenfaces. Let me show you what is that eigenface. So there are eigenvectors of the covariance matrix, and you will see that those eigenvectors will turn out to be looking like faces. That's why they are called eigenfaces. So this is a database called the Yale database, contains 165 images, 15 people, 11 images for each subject. Each of these images, okay, can be transformed into a vector, just like you calculated a vector for that hyperspectral data. You took out a pixel vector for every point in that hyperspectral data. Similarly, you can transform this matrix, this is a matrix, this is an image, a matrix, into a vector by concatenating the rows one by one, or by taking the row and making the column, then taking the second row and putting it below that, third row below that. Like that you can do an arrangement which is called technically as lexicographic arrangement of the rows or columns to obtain a vector from a matrix or a face image. So you can obtain vectors from all these face images, and you can take the mean of all these face images and obtain something like this. That is a mean face, whatever I wrote. So now you have to compute the covariance matrix from this mean face. So each of this is vector xi. Each of these faces is vector xi. This is mx or mu x. So I can again use that formula to calculate the covariance matrix. So if I use that formula, I will get the covariance matrix, and I can take the eigenvectors of this covariance matrix. So when I take the eigenvectors of the covariance matrix and I reshape those eigenvectors into matrices, those are vectors, right? I have transformed my data into vectors, which were actually images, which were matrices. And after transforming them into vectors, I got a covariance matrix. Now each row in that covariance matrix is an eigenvector. I have done an eigendecomposition of that covariance matrix, and I have calculated a matrix A. Okay. That matrix A is the eigenvectors of the covariance matrix. Now that eigenvector is a vector. I will reshape that vector into a matrix, which is this. So here what I have shown is eigenfaces corresponding to the greatest 50 principal components. Those eigenvectors are also called principal components. The eigenvectors inside this matrix A are also called principal components. And what I have done is I have reshaped those eigenvectors, which are actually vectors, into images, into matrices. And when I show them on a PC, they look like faces. And it turns out that I can represent any face, in my database as a linear sum of these eigenfaces. Why? Because I can write this now. X is a vector which is actually the original face, the face from the original database. How did I get that X vector? I took the original face in the database and I made it into a vector. Now I have used eigenvectors of the covariance matrix and I have used this equation. So in this equation, if you see, this is a linear combination of A into Yi. How can I write A into Yi? How do I write Ax equal to B? In terms of a linear combination of columns of A. How can I write this? Suppose I write this matrix A as composed of columns. Now can anyone tell me how to derive B1 by writing this thing as a linear combination of the columns of can I not write that vector B as equal to x1 into a1 vector plus x2 into a2 vector up to xn into an vector, where xi are scalars and a1 to an are vectors. So what are these a1 to an? They are the columns of A. What are inside the columns of A? Eigenvectors of C. What are eigenvectors? So I have written X as a linear combination of eigenvectors of the covariance matrix. So I can write any image as a linear combination of these eigenvectors. So I can now write, I can try to plot a reconstruction of this image by taking a linear combination of these eigenfaces. So if I do a proper reconstruction, I should get back the original image. So you take a look at the reconstruction done by only 10 eigenfaces and done by using 50 eigenfaces. So as you keep on increasing the eigenfaces, you get a better and better approximation to the origin. Right? So this is the way to represent data. So I have data which is 165 images. So you can think of those images as 165 bands of hyperspectral data, each band of size, some rows and columns. So there are 165 images. So maybe you can think of it as 165 bands, and each image having some rows and columns. It's the same thing what I showed you earlier. So this is representation of the data in terms of the eigenvectors of the covariance matrix of the data. Can I use it for recognition? So what I am trying to say is that these faces, these 165 faces, are not lying as a point in 165 into m rows into n columns dimensional real vector space. Okay. Just like a point x with 3 components lies in a vector space spanned by 3 basis vectors. This face is actually, the original face is actually a point in a 165 into m rows into n columns real vector space. So it is not lying in that big vector space. It is lying in a much smaller vector space. And that is called a subspace of the original vector space. And that subspace is spanned by these eigenfaces. That means these eigenfaces, you have already seen now what is the meaning of spanning a vector. When I use that term, a vector is spanned by basis vectors. What do I mean by that? When I write a vector x equal to a into a hat I hat plus b into j hat, what do? I write x vector containing 2 components as combination of the I hat basis and the j hat basis vector, right? So I am writing a vector as a linear combinations of the basis vectors. So similarly, you can think of these guys as basis images, and the original picture, which is this guy, as a point in that huge 165 into m rows into n column space, which can be actually spanned by only 50 eigen images. So this is the idea of representing the data. How can I use it for recognizing it? So suppose you have this test case and you want to get the closest case to this test case in your database to identify whether that person is there in that database or not, or who is that person. So you have a finite number of images in your database and you call one of the people whose images you have taken in the database and ask him to sit and take a picture of that person. So that person will be something like this. Okay. Turns out that that lady has closed her eyes while the picture was being taken. But who is this lady? When I ask that question, who is that lady? That means I am asking the question, to which particular image in the original database this image is closest to, in some sense, some mathematical sense, whether mean squared or error or whatever. So in some mathematical sense, which is that face to which this input face is closest to. Again, you can use eigenfaces. You can find out that decomposition from each face with respect to the eigenfaces. And the best decomposition you will get with this. That is the best reconstruction you will get with this. So you will say that you have recognized this person. So this is the closest image to this. Only difference is the eyes are open and the eyes are closed. So you have recognized that particular person. Similarly for this. This is the test face and this is the recognized face. So you can do classification with PCA where you don't know the number of classes in the data. That is the important thing. PCA doesn't make any assumption about the number of classes in the data. Even without clustering the data, even without knowing that what class each data point belongs to, or what is the categorization of the data, you can apply PCA on it. But suppose somebody tells you that these many classes are available and the data only belong to these many classes. Okay. So there are P number of classes and you are being given data. For example, there are two classes here and data points are clustered around the centroid of these two classes. So now you want to reduce the dimensionality of this data. You can apply PCA. You can apply PCA by assuming that you don't know that there are two classes in the data. You are only given this data and you don't know that there are two classes in the data. You can apply PCA. But suppose somebody gives you that information that there are two classes and I want to project this data onto two coordinate frames, then to which coordinate frame should I project? On this one or on this one? So this is my question. That suppose somebody tells you that there are two classes in this data, on which of the axes should I project? I should project on this one. Because if I project here, I can preserve the separation between the data points, even in the projected data. If I project here, the separation between the projected data is lost. So the projected data points merge with each other. So I cannot say that one point is distinct from the other one. Whereas if I project these data points here, then I will be able to separate those two projected data point clusters. So if I know the extra information that classes of data are given to us, or how many classes are there in the data, then I can do this kind of a transformation where the criteria for maximization is the ratio of between class distance to within class distance. So what do I mean by between class distance, within class distance? Let us see. So again we have this p number of classes, so C1 to Cp, and there are nj samples in the jth class. So there are p classes Cj, for example, j goes from 1 to p, and there are nj samples in the jth class. So if I sum all the nj samples, I will get n. That is the total number of samples available. So let this be the global mean that I can compute from all the data points. So I will calculate the global mean like this. And the mean of the jth class can be denoted as mu j. Right? So then I will calculate two types of matrices. But one is called the within class scatter matrix, and the other one is called between class scatter matrix. So within class scatter matrix, if you take a look, so you have seen those two different clusters there. So what I will do is I will compute mu j for this guy, so mu1, mu2, and I will use the points clustered around mu1 to compute the within class scatter matrix for this particular class and the within class scatter matrix for this particular class by using this formula. So Ri belongs to Cj. The data points belong to that particular cluster. J goes from 1 to p. Suppose here p is equal to 2. So you have two means, one mu1 and one mu2. So if you use the data points around mu1, you get the within class scatter matrix for class 1. Similarly, if you use the data points around mu2, then you get the scatter matrix for, or the within class scatter matrix for class 2. Now you can get the between class scatter matrix, that is using the distance between the two different classes. So you are using means of the classes and you are comparing it with the global mean. So you have a global mean for the data and you are comparing the individual means with that global mean. For example, for that data, the global mean is lying somewhere in the middle. The global mean will be lying here. So you are computing the distance from mu j to that global mean and mu1 to mu and mu2 to mu. So it is giving you the idea about separation between classes. And the first one is giving you the idea how well clustered each class is. Suppose this was distributed over a larger circle and this was tightly clustered around the centroid. Then it gives you that idea, that how much is the within class scatter for data points and how much is the between class scatter between the separate classes. So what should I maximize? So just graphically representing this, you can see. You want to compute within class, you have to compute these distances. This is mu1, this is mu2, then this is the set of within class distances. And if this is, so there is a global mean somewhere, and you have to calculate what is the distance between two different centroids. So what is the separation? How well separated are two different classes is captured by between class distance, and how tightly each class is clustered around its own centroid is given by the within class scatter matrix. And what I want to do is, I want to project the data in such a manner that the between class separation is higher and within class separation is lower. That means I am maximizing the ratio of between class distance to the within class distance. So if I maximize this ratio, then I will be able to project data such that discrimination among classes is preserved. That is the extra thing that I do over PCA. Again in LDA I will do the same thing, but the extra thing that I have done is I have managed to preserve the discrimination between classes, which I ignored when I took PCA. Because I did not have the information that to which class which data point belongs. That is the extra information I have when I am doing LDA. Again, LDA is a linear transformation. So what I will do is I will compute or maximize the Rayleigh coefficient, which is defined like this, where this is the between class scatter matrix and this is the within class scatter matrix, and these W's are the eigenvectors which can be computed by solving this generalized eigenvalue problem. So this is obtained by using this data covariance matrix. So lambda is a generalized eigenvalue I can obtain is will get a matrix W with which I can again multiply X, original X. There the matrix was capital A. Here it is W. And this matrix W will have size L cross B minus 1, where L refers to the number of bands in the image. So this has L cross B minus 1 dimension, and I can use this W and multiply it with X minus mu X to get Y, which is the LDA vector. Okay, just like I obtained Y when I multiplied A with X minus mu X. In PCA, I will multiply X minus mu X with W, where W are the eigenvectors obtained by solving this generalized eigenvalue problem, and I am using the between class scatter matrix and the between class scatter matrix and within class scatter matrix. Earlier I used the covariance matrix. So this is the only extra thing, and this achieves projection of data onto lower dimensions where discrimination among the classes is present. There is nothing else apart from the discrimination among the classes, which is extra over PC. So I am maximizing this Rayleigh coefficient. This is also called the Fisher criterion because this came from the mathematician Fisher. It's also called Fisher's linear discriminant. So this is taught in pattern recognition, statistical decision theory. So we use it for data dimensionality reduction in hyperspectral image processing. So we can show you some of the results that we have obtained using LDA on Indian functions. So just like I showed you that the contrast will fall as you take the eigenvectors in PCA. Similarly, the same thing happens here also. Only extra thing you have is the information that these are the ground truth labeling of each pixel into so many classes. So many classes are given to you. Each pixel belongs to that particular class, which is coded and shown here as a grayscale image. So there are 16 classes, I think, in this ground truth, and you can decompose it into these packets. Similarly, for another hyperspectral data view, the only extra thing is this ground truth image. Because you know that this pixel belongs to this class, and this pixel's class is different from this pixel's class, you can do a thing. So I think we'll stop here. We are exactly at 1, and I have not yet touched my deep learning part in the slides. What should I do? Shall we come back after lunch, or should I will try, but that is a separate entire set of slides. That requires fresh thought, which is not linked to this. It depends on the audience. Like if the audience wants to come back. So within 30 or 45 minutes, I can finish those slides. Up to the students, they might be feeling hungry. I always go by the students. So what should I do? You come back. So after lunch, we'll talk about classification more in detail, and that classification technique is the rage of the town today. And we will talk about convolutional neural networks, slightly different than the multi-layer perceptrons, and how to use convolutional neural networks. My student is going to demonstrate in the afternoon lab. So you can talk. So let us just start the second half of this presentation. So we talk about convolutional neural networks, and the interesting thing is that these networks have been shown to perform very well on very challenging tasks, and we have been using these uh, networks for our own research. And I will show you today some of the research that we do in our lab. And this is a very interesting application of computer vision, which you might not have seen earlier. So let me just start off by introducing what are convolutional neural networks. I will initially give background and motivation from visual neuroscience, and then come to the engineering aspects of convolutional neural networks. So let me just start with this slide where I acknowledge the inventors of CNN, or the ideas of behind CNN, that is Fukushima, who gave the first model neocognition. So if you open up the journals of pattern recognition and you see the old issues, you will spot in the 1980s, I think somewhere around 1986, network which was named as neocognitron by Fukushima. And there was a guy called Jan Licken in New York University. So he gave a network called the LeNet, or the Licken network. He has different versions of LeNet, and I think LeNet 5 is the version which broke some records, and he became famous for that. So he has a paper, I think in Proceedings of IEEE 1989, if I am not wrong, where he gave techniques for handwriting recognition, or recognition of digits, handwritten digits, using a standardized database called the MNIST database, or the US Postal Digits dataset. So the idea was to read checks online without human intervention. So to read the numbers on the checks which were written by hand, or to read the PIN code, or the zip code as they call it in the US, of letters, to do an automatic sorting, this LeNet was very successful. So it was actually a successful neural network in the real world. So Jan Licken is the guy who gave this. But what happened after that? He gave it in 1989. But up to 2010, 2007, something like that, it was not being used. And people did not think that this model could perform on other data sets also. It performed very well on MNIST, performed well on that USPS postal code data, but people thought that it will not do well on other things. The ideas in this LeNet are taken from neocognition. That is why I put this sentence here. And there was a Nobel in 1962, if I am not wrong, in the 1960s, was given to these two people, David Dubel and Austin Wiesel. So the thing that they did was they analyzed the visual cortex of infant cats or kittens, and they analyzed and found that the visual system of kittens who were kept blind after birth. You see, like a litter of kittens, then they are generally blind after birth. So they open their eyes after some days. And he analyzed, or these people analyzed their visual cortex when they were blind and when they opened their eyes. And I will show some of these ideas of simple cells and complex cells. Whatever he analyzed in those animals also hold true for human visual system. So this idea of simple cells and complex cells, which was actually there in this neocognitron, because it was proposed after this Nobel Prize. They tried to mimic simple cells and complex cells in engineering neural networks. So something came from visual neuroscience and entered engineering as LeNet or neocognitive. So today we will see a LeNet in action, and actually my student will demonstrate to you the performance of LeNet on MNIST data. It gives an accuracy of more than 98%. And how does it do so well? What is the idea that it uses, and what is the breakthrough idea that it uses, which has made it better than multi-layer perceptrons, is the thing that I will discuss in this slide. So the main idea is sharing of weights in a feed-forward neural network. Very recently, 2017 or 16, I think, or rather 2-3 years ago, there was a paper in IEEE Transactions Image Processing, which did something like LeNet, not using neural networks, but using PCA. It was called PCA net. I want to bring this point up because we discussed PCA in the morning, and I am discussing convolutional neural networks now. People may think that that was separate and this is separate. It was separate talk and this is separate. But the idea that you can extract features from data in a hierarchical fashion, okay, is the important idea that we should take away from this slide. So we want to discuss how to extract features in a hierarchical fashion, maybe using PCA. You can extract features from data by using PCA. So I can have a grid of feature map that I can calculate from data using PCA weights, okay, weights which are known to you, because weights in PCA are eigenvectors of the covariance matrix. What can you do when you learn the weights? Is there an advantage of learning the weights from the data? So that we will see, and how to learn weights, how many weights to learn, and what to do regarding pooling weights or sharing weights. So these are some few ideas which were breakthrough ideas, and they made the whole area of neural networks active again. So this is the second wave of neural networks after the 1990s and the 1980s. So we will look at the second wave, and that is the wave driven by convolutional neural networks. So what is the idea of convolution in a neural network? And this whole network is in the supervised learning model. That is, I have data and I have annotated data. I have labeled data. That means somebody tells me that this particular face belongs to this particular person. So there is a label attached with every image. So if I have 0 to 9 digits and I write a digit with my hand, then I scan that thing which I have written, take a picture of it, and then I show that picture to a computer, and the computer should tell me whether it is the digit 0 or 1 or 2 or 3, something like that. And to train that computer to understand whether it is 0 or 1, 2, 3, I will have a data set in which every image of 0 will be labeled with a 0. Every image of 1 will be labeled or given a label 1. So this is an annotated label data set or a labeled data set. That is why we teach the computer or the neural network to understand what is the pattern that it is seeing, and the network tells me or predicts that this is the pattern that I am seeing. That is why it is called a supervised learning model. So you supervise the network to tell you what is the actual pattern. So this is the visual neuroscience, not very clear, but I will try to say what is going on here. So this is the mammalian brain, and this is taken from Van Essen's work. So he, in those early days, in the 1995, particularly you can see a particular issue of Scientific American in 1995. If you have a library in which Scientific American comes, please take a look at 1995 issues. You will find one issue in which they have given the classification of the regions or the anatomy of the brain, the visual cortex, and what function is performed by which part of the brain. So this region, which is the region here, it's called the Brodmann area 17, just here. Suppose I trip and fall, and I fall exactly here. For 2 minutes I can't see anything. Lights will go out. Why the lights go out? Because I hurt my visual area. And that is the happening in V1. It also happens in V2, V3, V4, empty. Okay. It goes, it's a hierarchical processing. So the idea to take away from this slide is nothing or not everything gets processed by V1. You see something in V1 and then the stimuli goes forward. It goes to V2 and something else is extracted at V2. Something else gets extracted at V3. We'll look at what is extracted at V1. When you look at the letter A, capital A, you look at this edge, you look at this edge, you look at this corner, you look at this corner. So corners and edges are extracted by what is called simple cells in the region V1. Then when you see, suppose I see my finger moving like this, what do I see? That there is an object which is reflecting light against a static background, and that object is oriented along this direction. It is different from this object. It is different from this object. So it is oriented along this direction and it is moving over a static background. So all that information is getting processed in V2, which finds out motion, or it has cells which are receptive to motion. So the human brain accesses visual stimuli at different places and performs different functions from the same stimuli. Okay. The stimuli is the same. It is being recorded by the retina and it is getting processed in a hierarchical fashion in different places. So it is distributed processing, hierarchical in fashion. So these are the two things to take away from this. So there are several things. So the retina is recording the visual stimulus. From the retina it comes to the lateral geniculate nucleus. So from the retina it goes to the lateral geniculate nucleus. You see the time is 20 to 40 milliseconds. By the time it reaches here, 40 milliseconds or 50 milliseconds has elapsed. By the time the signal reaches here, 60 milliseconds have elapsed. Then further, 70, 90, 100 milliseconds. You approximately take 1 second to actually understand what is happening. So that is all happening because of some latency or some amount of time delay in the processing. So if you want to move a finger from the time you have actually seen that object, okay, I want to touch this keyboard, from the time I see that object to the time I move my finger to touch that object, the time is 250 minutes. I can go more deep into visual neuroscience. I used to teach in the classes, but let me just restrict myself to this. So the idea given by David Dubel and Wiesel, who got the Nobel in 1960s. Simple cells detect local features. Complex cells, they pool the output of simple cells within a retinotopic neighborhood. What is a retinotopic neighborhood? It is the neighborhood which you can process in a certain point of time. I cannot process everything in the visual field at a time. I can only process whatever is focused on the fovea of the retina. There is a spot on the retina called the fovea which is having the maximum amount of cones. There are two kinds of receptors, you might be aware, rods and cones. The maximum amount of cones are there in the fovea and they die out as you go away from the fovea. So when you look at an object, you are turning your head and you are trying to figure out the best angle by which you can focus that object onto your fovea. So if you are trying to read something, you are trying to move your head such that you get the best focused image onto the fovea. So on the fovea, you are looking at the object and you are looking only at a portion of the object, not the full object. So if you are given a full face, you are not looking at the whole face pixel by pixel like a computer. You are looking at very specific spots and you are looking at the region around that spot which is called the retinotopic neighborhood. So how to do this processing with networks, with neural networks, with machines? How to mimic this? Whatever is happening in the human brain, how to mimic this? So to mimic this, we need to create layers of cells or computation units or neurons. So we create cognitron and the neocognitron. So he was trying to mimic what these people had proposed after studying the neuroscience of mammals. So this is our retinotopic neighborhood. You see? That is being viewed by one neuron, and that same neuron is looking at the other place with another neighborhood. So we will mimic the simple cells with neuron layers, which will be further cooled. You see here, 4 of these cells are cooled to 1 cell. So as you go higher and higher, you are visualizing more and more of the original neighborhood. Suppose you had seen 4 points in the first image at layer 1. Then when you go to layer 2, you will be seeing 4 points of layer 1 in layer 2. That means 4 into 4. So 16 points of the original image in layer 2. So in layer 2 you are doing a hierarchical processing where you are looking at a larger neighborhood in layer 2 as compared to layer 1. So layer 1 is looking at a smaller neighborhood. So you are pooling the outputs of layer 1 in layer 2 to achieve robustness to scale. Try to relate it like this, that you have an object here and you have an object here. So it is the same object. So how to deduce that it is the same object? So if your local processing only happened, there was no layer 2, then you will say that this is a different object. This object is different from this object. So this robustness to scale happens when you pool the output of layer 1 to layer 2. So you are looking at layer 2 is looking at a reduced resolution of the input image. So the resolution falls as you grow higher and higher in the brain, and the resolution increases when you grow lower and lower towards the input. So this is to provide robustness to resolution or robustness to scale. The work was done in 60s and the Nobel came in the 80s. So the visual cortex consists of a hierarchy of simple, complex and hypercomplex cells. So the simple cells, they are sensitive to just the presence or the absence of light in a receptive field of the neuron. Every neuron comes with a receptive field. So if you shine some light on that receptive field, the neuron fires or the neuron spikes or it emits an action potential. So when it emits a voltage signal, the action potential is a voltage signal, maybe in millivolts or microvolts, whatever, which you can actually record with a microelectrode and see it on an oscilloscope. Okay. These people actually inserted microelectrodes into the visual cortex of mammals or cats and things like that, and they actually observed the spiking potential after shining a certain amount of light on the retina of the kittens. So what they observed is that some cells are having receptive fields where they just detect presence or absence of light. There are some other cells called complex cells which detect motion of an illuminated object across the receptive field. So if there is something which moves, which is an illuminated object which moves across the receptive field, it fires. The neuron fires or it emits an action potential. Higher up, the hypercomplex cells, they fire only when the stimulus falls at a certain angle. If it falls at 90 degrees on the receptive field, they fire. If it falls at 0 degrees, they don't fire. So it is orientation sensitive. So hierarchical processing is happening. One is at the lowest level, it is presence or absence, and the second layer it is motion, and the third layer it is angle of motion. So as you go higher and higher, richer and richer descriptions of the input visual stimuli is extracted from the visual data. That is the way the human brain functions. Why not mimic it in the neural network? How to mimic it in the neural network? The initial effort started in the 80s or the 1970s by the neocognitron. Today where are we? And why should I talk about all this 30 years down the line? Today we want to do all these things. shown that on this kind of data set, the LeNet, which is a simple convolutional neural network, which you can just write few lines of code and execute, and it works fantastically for that data set, or for German road signs, or for facial expressions. People have today shown that neural networks, by using such ideas that were present in the human brain, they can excel at these tasks. So you can get unachieved accuracies till date with conventional handcrafted feature and classifier methods and by using learned classifiers or learned feature extractors. So I'll come to that a little bit later. First, let us just look at this. So these neural networks, or whatever I'm talking about, they are applied to data containing local correlations such as images, speech, time frequency representations like speech spectrograms, RGB depth images, etc. What is the traditional approach in machine learning, which we have been studying since a very long time? There is an image or a video, and there is a feature extractor. What kind of feature extractor? A PC, an LD. Okay, and I can have more sophisticated features like a scale invariant feature transform, or a LBP or a histogram of oriented gradients, which were recently proposed, or I can have older kinds of feature extractors like foo moments. Okay, different kinds of moments I can extract from an image, and then I can classify whether that image belongs to a certain class or not. So those were the old kinds of features which were designed by hand. That means I had a formula for it. I had a mathematical expression for that features which I wanted to extract. I did not learn the feature from the data. Okay. I had a formula for it. I designed a PCA feature vector for my input data. I had a formula for extracting PC. But the problem is that if you have a classifier and a feature, then you have to train that classifier on those features which you extract. Those features which were extracted and the classifier which you trained were simple in nature. They were not deep. The support vector machines, which was very popular in the 90s and in the 2000s, was proven to be or shown to be a one-layer neural network, a one hidden layer neural network. Today we talk about neural networks containing more than 50 hidden layers. So as you have more and more hidden layers, the problem is that the amount of training, the parameters to train, they grow up exponentially. So if they grow up exponentially, how to have deeper networks, how to design deeper networks? People could not design deeper networks more than 2 hidden layers earlier. But now, because you have convolutional neural networks which have shared weights, you have less number of parameters, and now you can design much deeper networks and you can train them in less time, and you can actually achieve accuracies which were not achieved by this traditional method. So if you could not achieve the accuracy with a PCA SVM, okay, or something like LDA SVM, or HOG SVM, or SIFT SVM, then you can do better than this by using CNNs. So traditional approach, just I will have a caveat here that some of my slides are taken from the internet. They are not original. So features, they became very key to recent progress in recognition. And there were several hand designed features which came in the pattern recognition literature. Some of these are the new ones. So what should be the next step? Should we design better classifiers or should we design better features? That is the problem. Better the feature, better the classification. Better the classifier, worse the feature, still better classification. But where are you pushing it? SVMs can do only so much, and the features that we have extracted can only go so far. So in 2005 or 2007, these features, they kind of saturated. They could not do well on some of the more tougher problems. So I'll introduce what those tougher problems are. And then it was seen that if you start thinking about convolutional neural networks and try to build convolutional neural networks with computation which is now recently available, things like graphical processing units, GPUs, then you can actually beat these guys. thing that they were not doing with feature and SVM or something like that was that they did not learn the features. So here what we do is we learn a feature hierarchy all the way from pixels to the classifier. So the connections between the neurons are learned and the classifier is also learned. So each layer of neurons extracts features from the output of the previous layer. So hierarchical data processing is happening. And we are training all the layers jointly. So we are not training the classifier separately. We are not extracting features separately and training the classifiers on the extracted features, but we are learning the features and we are learning the classifier simultaneously. That is the process that happened now. So let us come to this idea of weight sharing. How to do this? For deeper networks, it becomes exponentially difficult because the trainable parameters increase. Suppose we have a neuron which is looking at this picture of Einstein and it is connected to all the pixels in this picture. So you see, each of these weights are unique. They are different. Your weights are denoted as Wij, a weight connecting a particular neuron in a particular layer with all pixels in this particular picture. If I wanted to connect this neuron to this picture, I will again connect exhaustively with all the pixels again. Is there a need to do that? Am I doing something like an overkill? Why should I have second neuron looking at all the pixels again? Where in the brain, one neuron is looking only at a small region in the picture. It is not looking at the entire picture. Then why am I processing like this? I should process locally. So one neuron should look at a local region. And another neuron should also look in a local region which is not overlapping with this region or overlapping slightly. I should not be exhaustively looking at all the pixels. First thing. What should be the weights of these guys? And when this neuron is looking at the entire picture, for example, or when I want to create a feature map where the neurons which compose the feature map, they look at the entire picture, this neuron is only looking here. I can have another neuron looking here, another neuron here, another here. And I can create a feature map which is the same size as the input image by tying all these weights together. These weights are different from these weights. These weights are different from these weights. These weights are different from these weights. They are not uniquely different. They are similar here. They are similar here. And they are similar here. So we are sharing weights and we are looking at local pixels. We are not looking brute force at all pixels and not sharing weights. Earlier we were doing this thing wrong. In multi-layer perceptrons, this is what you did. When it was a fully connected multi-layer perceptron, this is what you did. Now the change that I did in a convolutional neural network is that I tied up the weights, I shared the weights, and I looked at local regions, not at the full image. So what is happening here? I have layer M minus 1 and layer M plus 1. So layer M is looking at layer M minus 1, and these weights, you see, just look at the color. So these weights are same. These weights are same, blue. These weights are same. So we are looking at different neurons with the same weights. Ideally, in the hidden layer perceptron, what will we do? All the weights will be different. They will all be unique, and we will learn all the weights. So the weights will blow up. The number of weights will go on increasing exponentially. Here, the weights are not increasing exponentially. So why am I doing this weight sharing? What does it achieve? So features that are useful on one part of the image and probably useful elsewhere, they are learnt. All units share the same set of weights, and we do shift variant processing or shift translation invariant processing. So suppose I am looking for this eye region, okay, in my face. The eye has a very distinct pattern, and I am looking for this pattern in the face. My face can be a single picture in the whole picture, or it can be a part of a bigger picture where there are other objects in the bigger picture. So then, if I have a network which will only identify an eye and it will not look at different regions of the input image to look at where is the eye, then it will fail. This local processing, when you actually do this, you are moving this guy over the entire image. These weights are all common. So the weights are fixed. There is a kernel of weights, like a filter. Just like in image processing, you have a mask or a filter, a 3x3 mask. So you have a 3x3 mask which is being slid like a window over the entire image to produce a convolved output which is called the feature map, corresponding to one particular layer. So let me just come slowly and we will see how to generate feature maps. So we do a convolution with a learned kernel or a learned filter. That set of weights which I showed you with one color, that is a single filter. That is a single kernel or a single mask containing numbers. Those numbers are learned, they are not handcrafted. And there is no formula to generate those numbers in the masks. They are learned from the data. How to learn it? We start with random numbers, we do back propagation. We minimize the mean squared error. If you do back propagation, you start with random weights in the kernels and converge to some weights which will actually look like, if you ask me, Jabbar filter outputs. If you are aware of Jabbar filters can be tuned to detect features at certain orientations. Or they can look like high-pass filters that will extract edges from pictures. Why should they extract edges? Because our eyes are extracting edges when we look at something like this. Simple cells in the eyes are extracting edges, in the brain are extracting edges. So we should also have filters that will extract edges. High-pass filters, band-pass filters, Gabor filters. So all these filters which I showed you here, these colored weights, they will actually be high-pass filters. Those who are doing image processing, they will be aware what is a high-pass filter. Plus, we have to have a nonlinearity because our neurons are computational units which are nonlinear in nature. They are not linear computational units. So, we have a nonlinearity, and what kind of nonlinearity? People have experimented with sigmoid, tan hyperbolic, and they have come up with a new thing here which is called the rectified linear unit, which converges the training error much faster. I will show you plots. So, what we have here is that there is a input image X, there are some weights with which you convolve on the image and you get an output which, if you plot for all ij, becomes the same size as the input image and is called a feature map. And what I do is, at one level I have a feature map, I want to go to the next level. When I want to go to the next level, I will do this. I will do a pooling, which is called max pooling. So when I do max pooling, I will reduce the scale, or I will increase the robustness to scale. I will reduce the sensitivity to scale. So when I do this convolution, that is, I am looking for a pattern in that entire image by moving that kernel over the entire image and generating a feature. This is how it happens. So this is your first layer. This is the second layer. So the first layer is looking at different local regions of the image, and all these weights are the same. For a single feature map, all the weights are same. So you will get a single feature map. If you change the weights, you will get another feature map. So you can think of the first feature map being produced by a Gabor filter of orientation this. The second feature map being produced by a Gabor filter detecting orientation this. You can think of the first feature map as a high-pass filter generated using a high-pass filter, or a mask which can produce high-pass filtering of an image where the high-pass filter was detecting vertical edges, and the second feature map was the high-pass filter detecting horizontal edges. So you can learn high-pass filters. All these weights are learned. There is no formula. Just like you had a formula in the weights are learned. After learning and after doing the classification, after the training is over, you can plot what those filters look like. And those filters actually look like high pass filters or Gabor filters. I can show you some of our outputs. I'll try to rush, but let me see. So feature maps are produced by repeated application of a function across subregions of the entire image. So we do actually convolution. So that expression which I showed you, Aij equal to double summation Ij, Wjk, all that which I showed you, that was a convolution. So we are performing convolutions with weights. So that's why it is a convolutional neural network. And then we have, so there is a convolution operator here, you see. So on X you are performing convolution with a weight mask. This weight mask is learned and there is a bias. And this whole thing is passed through a nonlinearity, just like a nonlinear computational unit does. So this is the tan hyperbolic. You can use sigmoid, you can use ReLU. So this is more detailed explanation. If you see, these are the 2x2 weights which are being applied to generate different feature maps. So this weight will generate this feature map. This weight will generate this feature map. So 4 different feature maps are generated by 4 different weights. Let us look at these weights, how they look like. Why are we doing it? So one of the weights that looks like this is the Gabor filter. Gabor filter is nothing but exponential multiplied by a sinusoid. Okay. So an exponential is like a Gaussian. So a Gaussian multiplied by a sinusoid, how will it look like? Like this. And that Gaussian is oriented along this direction. If the Gaussian was oriented along this direction, you will get something like sinc function, almost like a sinc function. So a Gabor function with orientations along different directions can yield filtered images like this, where the output is emphasized along the direction of this Gabor. So this is actually the feature map. I'm plotting the feature map as an image. So whatever feature maps I showed you, this is one example. Then you come to the second layer, the higher layer. From the lower layer, I will do max pooling. So what it does is, it eliminates non-maximal values and it reduces computations for the higher layers. The higher layers will not do more computations, but it will reduce the amount of computations. So this is also what is happening in the human brain. And it provides a form of translation invariance. Provides invariance to resolution. So 2 things are happening: convolution and pooling. So that there can be 2 kinds of pooling. One is max pooling, one is sum pooling. That is, you can take the average of the neighborhood and get one number, or you can take the maximum of the neighborhood and get a number. So 2 kinds of things are happening. Activation functions, that is the nonlinearity. Nonlinearity can be a sigmoid. So this is the formula for the sigmoid. If you change A, you will get different slopes of sigmoids in 0 to 1. The big advantage of the sigmoid is differentiation. Why do you need differentiation? You want to do back propagation. So if you want to do back propagation, you want to find the derivative of the error, mean squared error. Derivative of the error you want to derive, and you want to find the derivative of the error with respect to the weight. Okay. So you have to train the weights. So here is the tan hyperbolic function, but people don't use sigmoid and tan hyperbolic these days. They use what is called the ReLU function, the rectified linear unit. This is also a differentiable function. It has this form. This is the derivative. And it has been shown in the recent literature that the ReLU function converges the training error much faster. This is tan hyperbolic training error. This is the training error with ReLU. So it reaches a 25% training error rate on this particular data set 6 times faster. So that's why people have shifted to ReLU. They don't use sigmoid or tan hyperbolic. Where has this idea succeeded? What has so changed or revolutionized the computer vision industry? This is the best result obtained on MS. This accuracy is better than the accuracy of an average human. So machines are doing better than humans at detecting digits, handwritten digits. This is the error in this particular paper. This is a object detection data set, object recognition data set. Traffic sign recognition. This is the error versus this error for humans. So machines are doing better than humans. And how to improve it for complex data sets. So what to do for complex data sets, that is the big thing that we are not now going to see. So let us just understand what was the network proposed by Yang, which is Leonard 5, which was that MNIST data set where I showed you 0.17% error. So this was your letter A. This entire image is of size 32 cross 32 pixels. Now there are 6 different feature maps. How are they obtained? By involving with this single input image 6 different filters. So I will have a mask which is of size say 5 cross 5. So there are 25 elements in that filter and there are 6 such filters. And I will create these 6 maps. Remember that in the beginning when I start the training, all the numbers inside these filters are random numbers. So when I begin, I have random numbers in the kernels. And when I finish training over a data set which is labeled, I will get feature maps which look like outputs of high-pass filters. So they are extracting edges. That is the most meaningful information here. The edge information, direction of the edge information, that is the most meaningful thing here. So that is what it will be extracted automatically. I never trained it to be a high-pass filter. It automatically learned to be a high-pass filter. Because the most meaningful information here can be derived by doing the high-pass filtering of this image. That is the magic of this convolutional neural networks. So you get feature maps here, 6 of the size 28 cross 28 because you are doing a convolution and you are not doing zero padding, so you get lesser size. Then you pool these. So there is a small neighborhood here. For this neighborhood, you get a single number. So you will get half the size of these feature maps. Same number of feature maps of size 14 cross 14. 6, 14 cross 14. 6. So now you have reduced from 32 cross 32 to 14 cross 14. Whatever was present here is also present here. You have taken care of resolution change. Suppose this was a bigger picture, this will also contain the same. So you have pooled, you have reduced the resolution. Then you again do convolution. With these, you again do convolution. So you apply one filter on this, you get one here. Apply another filter on this, you get another one here. Apply another filter here, you get another filter, another filter, another filter, another filter like that. Then repeat with different filters. So you will get more number of feature maps as compared to this. Here you got 6, you will have 16. You are doing convolution. Again, the filter kernels are random when you start the training. All of these are learning. They are getting learned. I will show you now a deep network where you can see what is being extracted here, what is being extracted here, what is being extracted here. It all happens automatically. And then here at the last layer, this is a fully connected layer, you will have an output which is only having 10 nodes, 10 neurons. So the neuron which was, for example, this is letter, here it is A, you can have something like 0 or 1 or 2 or 3 like that, and here you will have that particular label active during the test. During testing, you will get this particular label active. How do you train it? When you train it, if the input image is 0, all these things are random, then here the output will be the label 0. So you will clap the output with the label and the input image will be supplied, everything else will be random, you will run back propagation. You will reduce mean squared error. As you keep on reducing mean squared error, as you keep on applying different input images, mean squared error will keep on falling. And you will achieve convergence from random numbers to meaningful filters. This is something that you can see on his website. He has given a GIF. So you can actually see the animation. Then it's 5. So another one, Caltech 101. So here we has some data set of objects, and there are 100 classes. So he produces output as this is a very basic network. You see only 2 convolutional layers. Rest are pooling layers. So 2 convolutional layers produces very good results. Now let us come to a difficult problem. There are 14 million labeled images and there are 20,000 classes. Now this is an industry problem. This is some problem which the industry wants to crack. So if you have 14 million labeled images, you cannot work in academia and hope to crack this problem. You require specialized hardware, you require funding. And there are 20,000 classes to which these images belong to. There can be so many classes. And can you use 1.2 million training images, 1000 classes for example, and get a high accuracy? So this was done in CVPR 2009. This dataset is called ImageNet dataset. And this is the paper published in Neural Information Processing System. And this is the ImageNet classification with deep convolutional neural networks. This is not very deep. I think there are 7 convolutional layers here. You count, there will be 7 convolutional layers. And the paper is by Krizhevsky. So the company in which Krizhevsky was working was acquired by Google after he showed this result in 2012. So it is image recognition. The images are of different types: cats, dogs, urban landscape, bigger camera or a guitar or something, all objects. So there are 1000 classes. And this is the full network. So there is one convolutional layer here, another convolutional layer here, one more, 3, 4, 5. So for 5 convolutional layers, you beat the problem. 1000 classes, 5 convolutional layers, problem is gone. Okay? You can actually learn this. He ran it for 1 week over GPUs and it trained the entire thing. So again, these are the filter kernels. You see, this is the plot of the filter kernels after the training is over. So how do they look like? From random numbers, they start approaching kernels which are making sense. They are like band pass filters or high pass filters. So these are the images that were supplied. You just look at this image. There is a full image containing nothing, and there is this mite. And the machine has to declare that there is a mite in this picture. Even a human can miss this. There is nothing in the entire picture except only over here. It's a very tough problem. Okay? If you look at this, most of the picture is gone, only this or this. Very tough to understand. Very bad images, containing very bad illumination. So these were the retrieved images by the Krizhevsky's network. So if this was the test image, these were similar images that were extracted from the database. You see how tough it is. So how to visualize this convolutional neural networks? How to look at the layers, what the filters become after training. So at layer 1, you can see that they are becoming something like high pass filters. They are oriented edges. They respond to oriented edges. What happens in the higher layers? So if you see the higher layers, they are responding to dog faces, birds' legs, keyboards, dogs, textures. So higher layers are extracting things like texture, like things like legs, eyes, face parts, like mouths. So they are actually looking like that. So if you see the filter kernels at higher layers and you show them as an image, it will look like an eye, or it will look like a mouth part, or it will look like an ear, or it will look like a leg. So it is extracting object features. It is extracting features or parts of an object. So what did we do with C? So we thought that let us analyze the age-old problem of Indian classification a new thing that you can do in Indian classical dance which people have not done. And what we analyzed was, nobody has ever tried to understand what the dancer is performing if they don't know Sanskrit or if they don't know the language in which the shloka is being recited. So can you actually figure out the shloka from only video data, no audio data? So how can you figure out the dance performance that a dancer is doing? We have not solved this 100%, but we have made an effort. And I would like to show you some basic results, just photographs. These are some of our publications. So I had one PhD student, Aparna, who actually started working in 2015, and the first paper came in 2016. The second paper is 2018, the recent paper, and we have another book chapter also coming up in the book. So we took things like Indian dance is composed of hasta mudras, or static single hand gestures, which are called asanyukta hasta mudra and sanyukta hasta mudra. That is single hand static gesture and double hand static gesture. So sanyukta hasta mudra is double hand and asanyukta is single hand. And there are few classes which you can identify. You can also look at what is called body postures of dancers, which in Bharatanatyam are codified as karanas. And there are about 100 karanas in Bharatanatyam. We can identify body postures. We also looked at emotions in dance. Which emotions dancers emote, which are known as navarasas in dance. So there are 9 different rasas which the dancers use in their abhinay on their face, and they use hand gestures plus body postures to depict what is written in a shloka. So I will show you how a shloka can be decomposed into identifiable parts, which can be broken down into or decomposed into these hasta mudras and postures and emotions. So let me just quickly show you the paper. That's why I wanted to connect this laptop. So this was our paper, and the first paper was in signal processing. So these were the dance postures. So if you look at the dance postures, there was a lady who had actually studied these dance postures in Bharatanatyam. So forgot the name, I have the reference of this particular lady. So she is showing a particular karana, which is actually the Nataraj pose. And there is a particular pose in which she is standing here, which is called the Vardita Karana, which is actually a sculpture on the Chidambaram temple in southern India. So these sculptures, they are depicting these karanas, and you can see that they are almost identical. So can you identify the body pose by fitting skeletal structures to this? It turns out to be very difficult. So what I have done is I have shown the output or the failure cases of the best skeletal fitting algorithm in the world currently on Indian dance images. They just fail. Okay? Cannot work. Why they cannot work? Because of occlusions. See, this leg is occluded. This hand is occluded. Okay, it is a side posture. Here you see, it's very tough to identify this hand, this hand. It's very difficult to put a skeletal structure. You can see several papers where they have done it for running, jumping, sports, videos, they have been able to do for that. But for Indian dance, it doesn't work at all. So we used a simple network like what I showed you, the Lenet. And we recognize these postures. So she is Krishita. She came to our lab from Shivpur Engineering College. She worked and got a journal. So these are histogram of gradient features which we extract. We also use the Microsoft Kinect. So Microsoft Kinect can give you depth data. Microsoft Kinect, if you know, can also give you skeletal data. But it gives you skeletal data only when you are dressed like this, where this dress is short, the leg is visible. What happens for these cases? These are different types of currents. There are 14 different currents from YouTube videos which we collect. And these are the filter kernels that the filters got learned. So if you look at these filter kernels before training and after training. So these are the outputs of the filter kernels for extracting or identifying this posture, or this particular pose. So they are extracting something like edges, different types of edges. And this is the output with which we are comparing. You look at all these skeletal structures, all of them are wrong. This is the approach in some people. Even for this case, went wrong. It's much more controlled. Went wrong. We are not fitting skeletal structures, we are just identifying. And let me just show you quickly. These are the hand gesture data sets. So these are the Sanyukta Hasta Mudras. These are the Sanyukta Hasta Mudras. All this is data set captured in the lab. This is taken from the internet. Can we use this Hasta Mudras to understand a shloka? This is the Guru Stuti. Whatever we do. Guru Brahma, Guru Vishnu, Guru Maheshwar. That is that Stuti being performed by a famous dancer of Bharatanatyam, Manjuari. She is performing Mohiniyattam. This is a traditional attire of Mohiniyattam. And she is performing that dance with these Hastamudras. And we can decompose that entire video into these frames, these key frames, and identify these Hastamudras. And decipher the shloka. This is one paper. I'll show you one. This is about body postures and Hastamudras. This one is about emotions. Can you identify emotions in the abhinay of a dancing? So these were some of the emotions performed to us by Rishi dancers. Each emotion has ambiguities. Do you see? So there is a Vibhatsya Navarasa, which is performed in two different ways. There is a Hasya Navarasa, which is performed in two different ways. So this problem is difficult because each performer has a favorite way of performing that particular Navarasa. Again a linnet, simple linnet, and this is a 3D CNN, so we just forget about it. But these were some of the emotions performed by students in my lab. We took images, we also took depth maps using Kinect. And look at the clutter in the background, these curtains in the background. If you apply LBP, HOG, SVM, they go for a toss because of this clutter. And these were the outputs of the filter kernels that we learned in this first and the second convolutional layers. So they are extracting something like the high frequency regions in the image. How to characterize an emotion. This is the shloka. Using keyframes in this shloka, you can understand what are the emotions being performed by the dancer. And this is actually this shloka. So you can just see a little bit of the English translation, and you can just see where are the emotions. You can see this. You can see this. So these are translated into these kinds of emotions, which are there in our data set, and which can be identified by a trained skin. So these were the Navarasas which were identified. So first one is the Shringara Navarasa. Vibhatsa Navrasa, the Adbhuta Navrasa, the Bhayanaka Navrasa, the Hasya, Karuna. How can you use this to train dancers? Can you train inexperienced dancers by giving them feedback of how well they are performing these navrasas? You can put the model in a computer and you can put a webcam on the computer and make the dancers perform the navrasas in front of the webcam. Record their pictures and get real-time scores, because the neural network performs in real time, right? In the test mode. In the testing mode, it performs real time. So it will give you a score based on how well you have performed the navrasas. So that is the practical relevance of this work. So I'll end my talk with this. Do you have any questions? Any questions from the audience? I'm not very sure, but particularly in the recent years, I think we are one of the first people to address Indian dance